Welcome to your channel, Silent Mind Studio, and thank you for listening to us. This is the deep dive, where we really plunge into the sources you provide. We pull out the essential knowledge, helping you get up to speed quickly. Today, we're taking a really deep dive into something absolutely foundational. I mean, really the bedrock of modern technology, operating systems.
That's right. It's that, often invisible layer of software that makes everything work. Your phone, your laptop, even supercomputers.
Yeah.
They all rely on it.
It's like this hidden engine, incredibly complex, but its whole job is to make interacting with powerful machinery simple, or simpler anyway. And just a note, if you are interested in content like this, we'll be digging into fascinating topics like this pretty much every day, so stick around.
Definitely. And we've got a great set of sources for today provided by you, our listener, covering the whole story. From, the earliest ideas back in the 50s right up to what people are thinking about now. AI. Quantum computing. So our goal here is to really distill the key insights from all this material. We want you to come away understanding, what an OS actually is, why we even have them, what the main parts are.
How do you tell a good one from a bad one?
Exactly. How we measure quality and, crucially, where things are heading. It's a story of constant change, really. Always chasing efficiency, security, making things easier for people to use.
Okay, let's unpack this then. It's amazing when you think about it. You tap an icon on your phone, click something on your screen, and underneath that simple action, there's this incredibly complex system juggling billions of operations, managing hardware, keeping everything from crashing, most of the time anyway.
Yes, stability is key.
And the journey. Thinking back to when operating a computer meant physically plugging wires or feeding in stacks and stacks of punch cards.
Oh, absolutely. The contrast to today's seamless multitasking world is just staggering. And that history isn't just, a fun fact. It's completely tied up with the history of computing itself. It's about humans figuring out smarter ways to get work done with these powerful and back then astronomically expensive machines.
All right, let's set the time machine. Where does this story really begin?
The genesis from manual labs to batch processing.
So the very first hints of an operating system. We're talking way back, right? Before computers were anything like what we recognize now.
We're really looking at the 1950s for the first concrete steps. Before that, say in the 1940s, early 50s, computers were essentially bare metal. No OS layer at all.
Bare metal, meaning you had to prep the machine for every single job. Manually.
Exactly. Imagine these huge room-sized machines. You'd load your program and data, often using punch cards, maybe one job at a time. Or even worse, sometimes you'd physically wire up connections on a plug board, almost like an old telephone switchboard.
That sounds incredibly tedious and slow.
Incredibly inefficient is the word. Each program needed significant setup time. And as the hardware itself got faster, moving from electromechanical relays to vacuum tubes, then to transistors, this manual setup became an even bigger bottleneck. The machine could calculate quickly, but you spent ages getting it ready for the next task.
So the machines got faster, but the humans couldn't keep up with feeding them work.
Pretty much. This mismatch, this growing hardware complexity, combined with the sheer inefficiency of manual operation, created a real need for automation. That's when the first, very rudimentary OS-like software started to emerge, mid-1950s.
What were they called? Did they even call them operating systems?
Not usually at first. They were often called monitors or supervisors. Really simple programs. Their main goal was just to automate the transition between one job finishing and the next one starting.
Okay, so smoothing out the gaps, can we point to any specific examples from back then?
Yeah, the sources give us a few pointers. You see early efforts like LEOI in the UK, around 1951, which was a commercial development based on the earlier EDSSE. It started thinking about more organized ways to process jobs. But by 1955, you get more concrete examples. General Motors had an early operating system for their IBM 701 machine, and MIT developed something called the tape director for the UNIVAC 1103 around the same time.
What did those early systems actually do?
They were basically resident programs. They stayed in the computer's memory and handled simple tasks like loading the next program from tape or cards and managing basic input-output operations. It was the first step away from purely manual control.
Okay, so a move towards automated management kicks off in the mid-50s, but is there one system that people generally point to and say, okay, that was the first real OS?
It's a bit debated, as the sources mentioned. Defining the absolute first is tricky because things evolved gradually. But the GM-enabled system is very frequently cited as a major milestone, a real pioneering effort. That was developed in 1956 for the IBM 704 mainframe.
GMNAAIO sounds like a government agency. But significant? Who was behind it?
It was a collaboration. Robert L. Patrick from General Motors Research and Owen Mock from North American Aviation. And it actually built on some earlier work GM had done in 1955 for their previous IBM machine, the 701.
Okay, and why did they build it? Was it just pushing the boundaries of computing, or was there a more pressing need?
Oh, it was intensely practical. It came down to one thing, really. Money. Or rather, the cost of wasted time on incredibly expensive hardware.
The IBM 704 wasn't cheap, I imagine.
Not at all. Millions of dollars in today's money. And the way people used these machines back then, the open shop model, was just incredibly inefficient. Programmers would book time, come in with their deck of punch cards.
And spend most of their time setting things up.
Exactly. Loading cards, flipping switches, maybe mounting tapes. The sources mentioned a study at GM Research where someone allocated a 15-minute slot on the 704 might spend 10 minutes just on setup and teardown. That left only 5 minutes for the computer to actually, compute.
Wow, 2/3 of the time wasted. That's huge.
Huge costs in wasted machine time, as one source puts it. When you've invested so much in the hardware, having it sit idle most of the time is just not sustainable.
So the economic pressure was immense.
Absolutely. GMNAA IO was the direct answer. Its core function was to automate that transition between jobs. You prepare a batch of jobs ahead of time, maybe load them onto magnetic tape. As soon as one job finished, the GMNAA IO monitor program would automatically load the next job from the tape and start it running. No human intervention needed between jobs.
And that's batch processing.
That's the birth of batch processing, running jobs in a continuous sequence, a batch. It also provided shared, reusable code routines for controlling input-output devices, card readers, printers, tape drives, so individual programmers didn't have to write that complex I/O code themselves for every single program.
Which saved even more time and reduced errors.
Right. It streamlined the whole operation, making the entire facility much more efficient.
So this paints a picture of OS development as an evolutionary path. Starting with solving the most obvious bottleneck, the wasted time between jobs. Batch processing was the first big paradigm shift.
Yes, it was a huge step forward in terms of throughput, getting more jobs processed per day. But it had its own limitations.
Like what? You couldn't really interact with it, right?
Exactly. It's very non-interactive.
Yeah.
You submitted your deck of cards or your tape, and you waited maybe hours, maybe even days to get your printout back. There was no back and forth.
Okay. So what came next? Hardware kept getting better in the 60s.
Dramatically better.
Yeah.
And two key hardware advancements really enabled the next big leap. The development of hardware interrupts and more sophisticated I/O channels.
Interrupts. We'll need to unpack that, but they allowed for...
They allowed for multi-programming.
Multi-programming. Okay, does that mean running multiple programs literally at the same instant?
Not quite on a single CPU, no. But it meant having multiple programs resident in the computer's memory at the same time.
Ah, okay. Why was that useful?
Because programs, especially back then, spent a lot of their time waiting for data to be read from a slow tape drive, waiting for a line to be printed.
Waiting for I/O, input-output.
Right. And in a simple batch system, while one program was waiting for I/O, the expensive CPU was just sitting idle, doing nothing.
Wasting valuable time again.
Exactly. Multi-programming tackled this. The insight was, if the currently running program has to wait for I/O, the operating system can switch the CPU's attention to another program that is ready to compute, one that's already loaded in memory.
So it juggles multiple jobs, keeping the CPU busy as much as possible.
Precisely. When the first program's I/O eventually completed, the OS could then switch back to it later. This dramatically improved CPU utilization. You got much more useful work done in the same amount of time compared to running jobs strictly one after another.
That's a big efficiency gain. But still not interactive, right? Still submitting jobs and waiting.
Still batch-oriented, yes. The drive for interaction, for users to be able to talk to a computer directly, combined with the desire to share one very expensive mainframe among many users simultaneously, led to the next major evolution. Time sharing.
Time sharing, like everyone gets a little slice of the computer's time?
That's the core idea. You'd have multiple users connected to the central computer, typically through terminals, which were basically just keyboards and screens back then. The time-sharing OS would rapidly switch the CPU between all these different users' programs.
So rapid.
Very rapidly. Each user's process might get a tiny fraction of a second, a time slice, before the OS switched to the next user, often in a round-robin fashion. It happened so fast that it created the illusion for each user that they had the entire computer to themselves.
So you could type a command and get a response almost immediately.
Yes, that was the breakthrough. Interactive computing. It fundamentally changed how people could use computers for program development, text editing, problem solving.
Were there key systems that proved this concept?
MIT's CTSS, the compatible time-sharing system, was a landmark. It was first demonstrated in 1961 and became operational around 1963. It really showed the world that interactive time-sharing was feasible and incredibly powerful.
Okay, so that evolutionary path is clear now. Manual, then batch processing to automate job flow, then multi-programming to keep the CPU busy during I/O waits, and finally time-sharing to allow multiple users to interact with the machine concurrently.
And it's all driven by these core goals: maximizing the use of expensive hardware, minimizing the turnaround time for users, and supporting more applications and more users on a single system.
And you said this evolution was tied to hardware advances.
Inextricably. You couldn't do multi-programming effectively without hardware interrupts to signal I/O completion. You couldn't do time sharing without mechanisms to quickly switch between users and protect their programs from each other. New hardware features enabled new OS capabilities, and the demands of new OS paradigms pushed hardware designers to innovate further. It's this constant co-evolution.
A really powerful feedback loop. So just to quickly recap the fundamental why behind these early OS efforts, it was all about boosting efficiency, cutting down that expensive idle time, automating the tedious tasks operators had to do, and figuring out how to share these massive, costly mainframes among many different jobs or users.
Exactly. Transforming these giant calculators into more productive, more accessible tools.
Given how complex even these early systems sound, what were the key enabling factors? How were people able to actually build them back then? It seems like a huge leap.
It was a huge leap. And it really required a convergence of several things. First and foremost, you absolutely needed hardware advancements.
More than just faster tubes or transistors.
Yes, specific capabilities were crucial. The very idea of a stored program computer was fundamental. Machines like EAT-SAC and EAT-ISAC around 1949 were pioneers here. They could store not just data, but the program instructions themselves, in memory initially, using things like Mercury delay lines.
You can't have an OS managing programs if the OS itself can't be stored and run from memory.
Precisely. Then came better memory technology. The introduction of random access magnetic core memory, like in the IBM 701 in 1952, was a huge step up from sequential access like tape or the finicky delay lines. And as core memory got larger and cheaper through the 50s and into the 60s, it became possible to hold not just the OS monitor, but multiple user programs simultaneously, which was essential for multi-programming.
Okay, memory is key. What about those interrupts you mentioned being vital for multi-programming? How did that hardware actually work? What made it so special?
Right, the interrupt mechanism was truly a pivotal hardware innovation. Systems like the UNIVAC 1103A had it around 1956. Think of it like a doorbell for the CPU. Instead of the CPU constantly having to ask every device, "Are you done yet? Are you done yet?" It was called polling and waste tons of time. The hardware device itself could signal the CPU when it needed attention.
Like when a disk finished reading data.
Exactly. When the disk finished, it would send an electrical signal and interrupt to the CPU. The CPU would then automatically, usually after finishing its current instruction, pause whatever it was doing, save its current state, like the instruction pointer, and register values, and jump to a predefined location in memory where a special piece of OS code resided.
The interrupt service routine.
The interrupt service routine, or ISR. This routine would handle the event, maybe copy the data from the disk controller's buffer into main memory, update a status flag, and then the OS can decide what to do next. Maybe resume the program that was waiting for the disk, or maybe schedule a different program to run.
So interrupts allowed the OS to react to hardware events efficiently without wasting CPU cycles polling.
Absolutely fundamental for multitasking and time sharing. It allowed the OS to be event-driven. And complementing interrupts, especially in the 60s, were I/O channels, or sometimes called data channels. These are like dedicated mini processors just for handling input-output operations.
Taking the load off the main CPU.
Precisely. The main CPU could tell an I/O channel, okay, read 1,000 bytes from this tape, drive into this memory location, and then the CPU could immediately turn its attention to running another program's computations. The I/O channel would manage the slow, byte-by-byte transfer between the device and memory independently.
And it would interrupt the CPU only when the whole transfer was done.
Right. This ability to have computation and I/O happening concurrently, orchestrated by the OS using interrupts, was a massive boost to overall system throughput.
Okay, interrupts and IO channels handle the flow, but with multiple programs in memory, how do they stop them from messing with each other? Memory protection sounds critical.
Utterly critical. You absolutely cannot have multi-programming or time-sharing without hardware-enforced memory protection. Otherwise, one buggy program could accidentally overwrite the data of another program, or worse, corrupt the operating system kernel itself, crashing the whole system.
How did they do that early on?
Early techniques were relatively simple. Things like base and limit registers, special hardware registers defining the start address base, and the size limit of the memory region allocated to a program. The hardware would check every memory access to make sure it fell within that program's allowed range. Systems like IBM's OS 360 used memory partitioning, dividing memory into fixed or variable-sized regions for different jobs. But the real game changer came with systems like the Atlas computer, which pioneered hardware support for virtual memory with paging.
We'll need to dig into virtual memory later, but that provided better isolation.
Much better. Paging allowed the OS to give each process its own private address space, making it impossible for one process to directly access the memory of another unless explicitly allowed through sharing mechanisms. The hardware, the Memory Management Unit, or MMU, handled the translation from virtual addresses used by the program to physical addresses in RAM, enforcing protection along the way.
So the hardware foundation was laid with stored programs, better memory, interrupts, I/O channels, and crucially, memory protection. What about the software side? Writing an OS seems much harder than writing a single application.
It is, and advances in software concepts and programming tools were just as vital. In the very early days, people programmed in raw machine code, or maybe assembly language. Imagine writing tens of thousands of lines of low-level instructions.
Tedious and incredibly error-prone.
Absolutely. The development of assemblers, which translate symbolic assembly code into machine code, loaders, which load programs into memory, and especially compilers for higher-level languages, made a monumental difference.
Like Grace Hopper's work on the first compiler, the AZER system you mentioned.
Exactly. And John Backus, leading the team for Fortran in the mid-50s, compilers let programmers write code in languages that were much closer to human language or mathematical notation, abstracting away the gritty details of the specific computer's instruction set. This made it feasible to write much larger, more complex programs like operating systems. In fact, some early OS-like systems were built specifically to support these new languages. The Fortran Monitor System, FMS, on IBM machines was basically an OS designed to streamline the compiling and running of Fortran programs.
And the idea of reusing code.
That was emerging too. Reusable code and subroutine libraries became important. Instead of every programmer writing their own code to, say, read a punch card, standard routines could be written once and shared. Early computer user groups, like Share for IBM users, played a big role in developing and distributing libraries of common subroutines, especially for I/O.
Precursors to modern device drivers in a way.
In a sense, yes. It was the beginning of abstracting hardware interactions into reusable software components. The Share operating system, SOS, from 1959, explicitly aimed to manage I/O devices and data buffers, showing this trend towards standardized, reusable system software.
Okay, so we have capable hardware and we have improving software tools. What was the missing ingredient?
Innovative thinking. The vision and ingenuity of the people involved. The sources list many key figures: Gene Amdahl, Grace Hopper, John Backus, Fernando Corbato, Edsger Dijkstra, Ken Thompson, Dennis Ritchie, Tom Kilburn, Patrick and Mock, Fred Brooks. These individuals and the teams they worked with didn't just use the tools. They synthesized ideas, applied concepts creatively, and solved fundamentally new problems in managing computation.
Like that example of Robert L. Patrick using Gantt charts, a project management tool, to visualize parallel processes for GMNEA I/O. That's thinking outside the box.
It really is. It shows they were drawing inspiration from wherever they could find it to tackle the unprecedented challenge of automating and managing these complex machines.
Let's circle back to the initial uses. Where did these very first operating systems actually get deployed? Who used them?
Well, given the cost of mainframes, the users were initially limited to very large, well-funded organizations. Batch processing systems were heavily used in universities and research labs for large scientific and engineering computations. Think physics simulations, weather forecasting models, complex calculations, tasks that chewed up CPU time and were perfect for batch runs. FMS, the Fortran Monitor System, was a prime example in this space. Large corporations adopted batch processing for business data processing, running payroll for thousands of employees, managing vast inventories, processing bank transactions, generating customer bills. These high-volume repetitive tasks were ideally suited to the batch model. The military and government were also major early drivers and users. Cryptography, calculating missile trajectories, running simulations for defense or logistics, processing census data. These often pushed the limits of computing power and required sophisticated for the time management, which the rudimentary OS provided. And the OS itself was primarily focused on resource management. On systems like the IBM 700 series or the later System 360, the OS's job was to manage the allocation of the CPU, memory, tape drives, printers, etc., among the different jobs in the batch queue. OS 360, for example, explicitly supported multi-programming and memory partitioning to manage these resources more effectively. Then, with the advent of time-sharing, academic and research environments again led the way. Systems like CTSS at MIT and later Multics allowed multiple researchers or students to interact with the central computer simultaneously, sharing its resources for program development, data analysis, and communication. This is a huge shift towards more interactive and accessible computing.
You also mentioned that surprising example of airline reservations.
Right. IBM's Airline Control Program, ACP, from the late 60s. It was one of the earliest large-scale transaction processing systems. It used OS concepts to handle a high volume of real-time requests for flight bookings from terminals across a network. It showed OS principles being applied beyond pure computation or simple batch processing, moving towards real-time business applications.
So the initial applications really centered on maximizing the utility of these incredibly expensive machines for computation, data processing, and eventually shared interactive access.
Absolutely.
Right.
And those fundamental drivers, efficiency, automation, resource sharing, handling complexity established back then, are still shaping how operating systems are designed and used today.
It's incredible to see the seeds of everything we use now planted so early on. This has been a fantastic look at the genesis. If you are interested in content like this, by the way, we explore topics that intrigue us like this every day. And if you're finding this deep dive valuable, please consider subscribing to the channel and following us. We really appreciate the support. Also, if you are curious about this topic or have any questions as we go, please do ask in the comments section. We love discussing this stuff, so it's very exciting for us to hear from you. All right, when we come back, we'll dig even deeper into some of those key technological leaps and the influential figures who made them happen.
The architects and innovations behind early operating systems.
Welcome back to the deep dive. We've covered the why and the initial what of early operating systems, the move from manual operation to batch, and the first glimmers of multi-programming and time sharing. Now let's really zoom in on the specific breakthroughs and the brilliant minds drawing on our sources that propelled this evolution forward.
Absolutely. Building on that foundation, the period roughly from the late 50s through the 70s was incredibly fertile. Key concepts that are still fundamental today really took shape, enabled by specific advances in both hardware and software thinking.
Let's revisit some of those enabling technologies we touched on, maybe in a bit more detail. You mentioned stored program computers and memory advancements being critical.
Right. The source material really underscores this. Early memory technologies like mercury delay lines were not only limited in capacity, but also sequential. You had to wait for the data to circulate around. The shift to random access magnetic core memory in the early 50s, pioneered in machines like the IBM 701, was a game changer.
Random access meaning you could jump directly to any memory location.
Exactly. Much faster access to both instructions and data. And then crucially, as core memory technology matured through the 60s, it became larger and more affordable. Having more RAM meant you could load a more sophisticated OS and critically multiple user programs into memory at once. Without sufficient RAM, multiprogramming just wasn't practical.
Okay, memory capacity and speed were vital. Let's go back to the interrupt mechanism. You said it was essential for multiprogramming and time sharing. Can you elaborate on why it was so transformative? What problem did it solve?
It solved the problem of the CPU wasting time waiting or checking. Before interrupts, if the CPU needed data from a slow device like a tape drive, it either had to sit idle waiting for the data, synchronous I/O, or it had to constantly check a status flag. Is the data ready yet? Is it ready now? Polling. Both were incredibly inefficient. Interrupts flip the model. The hardware device signals the CPU when it needs attention. CPU can be busy executing another program's code. When the I/O device finishes its task, it sends that interrupt signal. The hardware forces the CPU to pause its current work, save its context.
Its current state, like where it was in the program.
Right, it registers, the program counter. And then it jumps to the OS's interrupt service routine. The OS handles the event quickly, maybe moves the data, signals the waiting program that its data is ready, and then the OS scheduler can decide which program runs next. It might go back to the interrupted program, Or it might switch to the program that was waiting for the I/O, which is now ready to run.
So it enabled the OS to efficiently juggle tasks based on external events.
Precisely. It's the foundation of asynchronous operation and responsive multitasking. Without hardware interrupts, modern operating systems simply couldn't work the way they do.
And I/O channels took this a step further.
They did, particularly for large data transfers common in mainframe environments in the 60s. An I/O channel acted like a specialized coprocessor for I/O. The main CPU would just give the channel a command block saying, transfer this much data between this device and this memory address. The channel would then manage the entire transfer autonomously, byte by byte, freeing the main CPU to execute instructions from a different program entirely.
True parallelism between computation and I/O.
Yes. The channel would only interrupt the main CPU when the entire transfer was complete. This dramatically increased system throughput, especially on I/O-heavy workloads. It fundamentally changed OS design in the 60s, making concurrent processing a reality.
And memory protection hardware became non-negotiable with multiple programs coexisting in memory.
Absolutely essential for stability and security. We mentioned base limit registers and memory partitioning as early methods, but the introduction of hardware support for virtual memory and paging, notably in the Atlas computer, was revolutionary.
Explain paging a bit more simply. How did that help protection?
Paging breaks a program's view of memory, its virtual address space, into fixed-size blocks called pages. Physical RAM is also divided into same-size blocks called frames. The OS, with hardware help from the Memory Management Unit, MMU, maintains a page table for each process. This table maps the process's virtual pages to physical frames in RAM. The key for protection is that each process gets its own independent page table and virtual address space. Process A literally cannot generate a memory address that maps to Process B's physical memory unless the OS explicitly sets up shared memory pages. The MMU enforces this boundary on every single memory access. It's a powerful isolation mechanism.
Prevents chaos.
Prevents chaos, yes. And it also enabled virtual memory, allowing programs larger than physical RAM by swapping pages to disk. But the protection aspect was critical for making multi-programming and time-sharing safe and reliable.
And all this complex software needed more reliable hardware too, right? The move to transistors and integrated circuits.
Definitely. Vacuum tubes were notoriously unreliable and generated a lot of heat. Transistors and later ICs were smaller, faster, consumed less power, and crucially, were far more reliable. Building a complex multi-component OS that needed to run for extended periods became much more feasible when the underlying hardware wasn't constantly failing. Reliability paved the way for complexity.
Okay, that reinforces the hardware's role. Now let's spend some time on those influential figures mentioned in the sources. Let's start with Gene Amdahl. What were his key contributions?
Gene Amdahl was a giant in computer architecture, especially during his time at IBM. He was lead architect on the IBM 704, the 709, and the hugely influential System 360 family.
System 360 was groundbreaking because it was a family of compatible computers, right?
Exactly. Before that, programs written for one computer model often wouldn't run on another, even from the same company. System 360 aimed for compatibility across a range of machines with different performance levels and prices. This meant you could run the same operating system, OS 360, and applications across the line. It was a massive undertaking and changed the industry. Amdahl also made fundamental contributions to CPU design concepts that boosted performance, like instruction pipelining, overlapping the execution stages of multiple instructions, instruction look-ahead, and the use of cache memory, small, fast memory to hold frequently used data. These are still core concepts today. And of course, he formulated Amdahl's law, which provides insight into the theoretical speed-up limits when parallelizing tasks very relevant for OS design on multi-core processors.
A true architect. What about Grace Hopper? We mentioned her compiler work.
Admiral Grace Hopper was a visionary. Developing the A0 system in 1952, widely considered the first compiler, was monumental. She passionately advocated for machine-independent programming languages, leading the charge for COBOL.
Why were compilers so critical for OS development?
Because writing large, complex software like an OS in assembly language is incredibly difficult, time-consuming, and prone to errors. Compilers allowed programmers to write in higher-level languages, closer to human logic, making it feasible to build much larger, more sophisticated, and more maintainable operating systems than would have been possible otherwise. They raised the level of abstraction.
Makes sense. And John Backus, another IBMer.
John Backus led the team that created Fortran in the mid-1950s. It was the first widely adopted high-level programming language, primarily for scientific and engineering computation. Its success created a demand for systems that could efficiently run Fortran programs, directly leading to OS-like systems like IBM's Fortran Monitor System, FMS, which automated the process of compiling and running batches of Fortran jobs.
Moving over to MIT, Fernando Corbato, key for time sharing.
Absolutely. Corby, as he was known, was the driving force behind both the Compatible Time-Sharing System, CTSS, and the ambitious Multics project. CTSS was the practical demonstration that interactive time-sharing could work, allowing multiple users to share a mainframe effectively. It was hugely influential. Multics, though complex and maybe not a commercial success in itself, was a groundbreaking research project. It explored many advanced OS concepts like hierarchical file systems, dynamic linking, and a strong focus on security. Many ideas from Multics profoundly influenced later systems, most notably. Exactly. Which brings us to Edsger W. Dijkstra. His contributions were more theoretical, but deeply impactful. Dijkstra tackled the fundamental problems of concurrency, how to manage multiple processes that need to cooperate or share resources without interfering with each other in harmful ways. He introduced concepts like semaphores for synchronization, preventing race conditions. His work on the multi-programming system demonstrated a layered, hierarchical OS structure and rigorous approaches to proving correctness. He also championed structured programming, arguing against the chaotic use of JO2 statements, promoting disciplined coding practices essential for building reliable, complex systems like OS.
Foundational concepts for managing complexity. And then, the legends from Bell Labs, Ken Thompson and Dennis Ritchie.
A pivotal duo, inspired by Multics but aiming for something simpler and more practical. Ken Thompson, with Dennis Ritchie and others, created UniX in the late 60s and early 70s. It was designed to be elegant, portable, and powerful. Dennis Ritchie also developed the C programming language, initially for rewriting the UniX kernel. C hit a sweet spot. It provided low-level access to memory and hardware needed for systems programming, but with the structured features of a higher-level language. It became the dominant language for writing operating systems for decades.
And the UniX philosophy itself was influential.
Immensely. The idea of having many small, simple tools that do one thing well and combining them using pipes to perform complex tasks. The emphasis on a hierarchical file system representing devices as files and its relative portability. UniX and its descendants, Linux, BSD, macOS, dominate large parts of the computing landscape today.
The impact is undeniable. What about Tom Kilburn over in Manchester, UK?
Professor Tom Kilburn led the team that built the Atlas computer and its operating system, the Atlas Supervisor, operational in the early 1960s. Atlas is often cited as one of the first truly modern operating systems because it introduced several key innovations years ahead of their time. Most notably, it pioneered virtual memory, which they called one-level store, using paging hardware. This allowed programs to behave as if they had a much larger memory space than physically available, with the OS automatically swapping pages between core memory and slower drum storage. It also implemented multi-programming and sophisticated scheduling. Many consider Atlas a major milestone in OS history.
Virtual memory, that's a concept we definitely take for granted today. We already discussed Robert Patrick and Owen Mock for their practical work on GMNAAIO.
Yes, their contribution was crucial in demonstrating the economic necessity and practical benefits of automating job processing, kicking off the whole batch processing paradigm.
And finally, Fred Brooks. He managed the OS 360 project.
He did. Fred Brooks managed the development of both the groundbreaking IBM System 360 hardware and its equally ambitious operating system, OS 360. This was one of the largest and most complex software projects ever undertaken at the time. His experiences managing this massive effort led him to write the classic book, The Mythical Man-Month. It contains timeless insights into the challenges of software engineering and managing large projects, like the fact that adding more people to a late software project often makes it later. His observations on communication overhead, system design, and the inherent difficulties of software are still highly relevant to OS development today.
So, putting it all together, these individuals and their teams really represent that intersection of hardware innovation, algorithmic breakthroughs, software engineering discipline, and the practical drive to solve real-world computing problems.
Absolutely. Their collective work laid the conceptual and practical foundations upon which all modern operating systems are built.
Let's revisit those early applications again, but maybe add a bit more color based on the sources. Batch processing was king for scientific and engineering work. Give us some specific examples.
Sure. Think about complex simulations, maybe modeling airflow over a wing for aircraft design, or simulating nuclear reactions. These required immense computation but no user interaction during the run. University physics departments, national labs, aerospace companies, they relied heavily on batch systems running Fortran code, often using systems like FMS to manage the workflow. Engineering firms would use batch for tasks like complex structural analysis calculations for bridges or buildings.
And the business world embraced batch, too.
Oh, yes. For large companies, it was essential for business data processing. Think about a large bank processing millions of checks overnight, or a manufacturing company running its entire inventory system, or an insurance company calculating premiums and processing claims, payroll systems processing paychecks for thousands of employees. These were perfect batch applications, high-volume, repetitive, data-intensive tasks that could be queued up and run efficiently overnight or during off-peak hours.
And the military and government applications.
They were pushing the boundaries. Besides cryptography and ballistics, think large-scale logistical simulations, analyzing intelligence data, processing census results. Government agencies were often among the first and largest customers for mainframes, driving demand for machines capable of handling massive data sets and complex computations, which in turn required OS capabilities to manage them.
Universities weren't just users, but also developers and research centers.
Exactly. Places like MIT with CTSS or Manchester with Atlas use these systems not just for research computation, but as platforms for research into operating systems themselves. They were test beds for new ideas like time sharing and virtual memory. And of course, they were used to teach students about these emerging concepts.
And the airline system ACP stands out as an early example of something different.
Yes, IBM's airline control program was significant because it represented an early move towards online transaction processing. OLTP. It wasn't just processing batches of data, it was handling real-time requests from terminals across a network to check availability and book seats. It needed to manage concurrent access to shared data, the flight inventory, and provide relatively quick responses. It foreshadowed the kind of real-time interactive systems that are commonplace today. There were also early uses in process control, like monitoring and managing industrial processes, although dedicated real-time operating systems, RTOS, came a bit later.
So looking across these early uses, scientific number crunching, business data processing, government needs, research, early transaction systems, the common thread is using the OS to make these powerful, expensive machines manageable and productive for complex, large-scale tasks.
Precisely. And the fundamental requirements revealed by these applications, efficiency, reliability, managing concurrency, handling I/O, providing interfaces, are still the core challenges that operating systems address today, just at a vastly greater scale and complexity.
It's truly fascinating how those early needs shaped the entire field. Okay, we've thoroughly explored the roots. So what does this rich history mean for the operating systems running on your devices right now? This is where it gets really interesting, understanding the pieces that make up a modern OS. And a reminder, if you are enjoying this deep dive into the world of operating systems, please do subscribe to the channel and follow us. It helps us keep bringing you content like this. Also, feel free to drop any questions or comments below. We genuinely enjoy the interaction.
Deconstructing the modern OS.
Welcome back to the deep dive. We've journeyed through the history, met the pioneers, and seen the origins of operating systems. Now let's shift focus to the present day. Let's take apart a modern OS, like the one running on your phone or laptop right now, and see what's inside. What are the essential components?
Modern operating systems are incredibly complex pieces of software, as the sources make clear. They're not one single program, but rather a collection of interconnected components working together. Think of it as a sophisticated system, with each part having a specialized role in managing the computer's resources and providing services.
Where should we start? What's the absolute core?
That would be the kernel. The kernel is the heart, the nucleus of the operating system. It's the bridge between the software applications you run and the physical hardware, the CPU, the memory chips, the storage drives, the network card, everything.
It's the main controller.
It is. It runs with the highest level of privilege in the system and is responsible for the most fundamental tasks. Managing memory allocation, scheduling which processes get to use the CPU, handling communication with hardware devices, responding to those hardware interrupts we talked about, and processing system calls from applications. It's the first major part of the OS to load when the computer boots up, and it stays resident in memory the entire time the system is running.
I understand kernels themselves can be designed in different ways. The sources mention monolithic, microkernel. What's the difference?
Right. The kernel's internal architecture is a fundamental design choice with big implications. The sources describe a few main approaches. First, the monolithic kernel. Think of this as the all-in-one approach. Most of the core OS services, process management, memory management, the file system, device drivers, networking stack, are all bundled together into one large single program, the kernel itself. This entire program runs in a privileged mode, often called kernel space.
What are the pros and cons of that?
The main advantage is typically performance. Because all these components are tightly integrated within the same address space, they can communicate with each other very efficiently through simple function calls. The big disadvantage is robustness and maintainability. A bug in any single component, say a faulty device driver, can potentially crash the entire kernel, bringing down the whole system. Also, modifying or extending a large monolithic kernel can be complex. Linux is a classic example, although modern Linux uses loadable kernel modules to add some flexibility. Then you have the microkernel approach. This philosophy is about making the kernel itself as small and simple as possible. The microkernel only contains the absolute bare minimum essentials, typically basic process scheduling, memory management fundamentals like address spaces, and inter-process communication IPC mechanisms.
So where do all the other services go? File systems, drivers?
They're moved out of the kernel and implemented as separate processes called servers, running in user space, just like regular applications. These servers communicate with the microkernel and potentially each other using IPC messages.
What's the benefit of that? Sounds more complicated.
The benefits are primarily modularity, security, and reliability. If a device driver running as a user space server crashes, it only affects that server process. It's much less likely to crash the core microkernel or the entire system. You can potentially stop, update, or restart individual server components without rebooting. The downside is performance. Communication via IPC messages between user space and the kernel is significantly slower than direct function calls within a monolithic kernel, so there's often a performance overhead. Finally, there's the hybrid kernel. As the name suggests, this tries to get the best of both worlds. It keeps more services in kernel space than a pure microkernel to improve performance for critical functions. But it might still run some less critical services, perhaps some drivers or file systems, as user space servers, or use a modular design internally to gain some of the flexibility and robustness benefits of the microkernel approach.
Where do Windows and macOS fit in?
Modern Windows, based on the NT kernel, and macOS, using the X and U kernel, which blends mock microkernel concepts with components from BSD UniX, are generally considered hybrid kernels. They try to strike a balance.
So the kernel architecture is a really fundamental trade-off between performance, stability, and flexibility.
Exactly. There's no single right answer. It depends on the design goals of the OS.
Okay, moving on from the kernel. Memory management sounds like another huge responsibility, keeping track of what program is using which bits of RAM.
It's absolutely critical and incredibly complex. The memory management component of the OS has several key jobs. First, it needs to allocate memory to processes when they start up or request more, and then deallocate it when they terminate or release it, ensuring the memory can be reused. Second, it must protect memory. It needs to ensure that each process can only access its own designated memory space and cannot interfere with the memory used by other processes or, crucially, by the OS kernel itself. This prevents crashes and security breaches. Third, it often manages virtual memory, creating the illusion that the system has more memory than the physical RAM installed.
Right, you mentioned that virtual memory concept earlier, using disk space as an extension of RAM. How does the OS manage that swapping?
The most common technique is paging. The OS divides a process's virtual address space, the memory addresses the program thinks it has, into fixed-size blocks called pages. Physical RAM is divided into same-size blocks called frames. The OS maintains a page table for each process, which acts like a map, translating the virtual page numbers used by the program into the physical frame numbers where those pages are actually stored in RAM. If a program tries to access a page that isn't currently in RAM because it was swapped out to disk or perhaps never loaded yet, this triggers a page fault interrupt. The OS's page fault handler then takes over. It finds a free frame in RAM, or potentially selects a frame currently in use by another page, writes that page out to disk if necessary, this is swapping out, loads the required page from the disk into the frame, updates the page table to reflect the new mapping, and then resumes the program.
So it's constantly juggling these pages between RAM and disk based on what's being used.
Yes, using sophisticated algorithms to decide which pages are good candidates to swap out, like least recently used pages.
This allows you to run more programs or programs that require more memory than you physically have, although accessing pages from disk is much slower than accessing RAM, so excessive swapping, called thrashing, can severely degrade performance.
And memory allocation itself. How does it decide where to put things?
There are various techniques. Static allocation might happen when the program is loaded. Dynamic allocation happens during runtime when a program requests memory, like using malloc in C, often from an area called the heap. Allocation can be contiguous, giving the process one single block of memory, or non-contiguous, like with paging, where a process's pages can be scattered throughout physical RAM. Segmentation is another approach, dividing the address space into logical segments like code, data, stack.
And protection is built into this. Absolutely. The Memory Management Unit, MMU hardware, controlled by the OS, checks every memory access. Using the page tables, or segment tables, it ensures a process only accesses addresses within its allocated pages segments and enforces permissions, like read-only for code pages, read-write for data pages. Techniques like address space layout randomization, ASLR, also help security by making it harder for attackers to predict where specific functions or data will be located in memory.
Okay, memory management is incredibly intricate. How does this relate to process management?
They're tightly linked. When you run a program, the OS creates a process, which is basically the program and execution, along with its current state, CPU registers, memory contents, open files, etc. The process management component is responsible for the entire lifecycle of these processes.
Lifecycle, what do you mean?
It handles creating new processes when you launch an app, scheduling them to run on the CPU, managing their execution, coordinating their interaction, like communication or synchronization, and finally terminating them when they finish or are closed.
You mentioned processes have different states.
Yes. A process isn't always running. It can be in several states. New, just being created. Ready, in memory, waiting for its turn on the CPU. Running, currently executing instructions on the CPU. Waiting or blocked, pause, waiting for some event like I/O completion or a signal from another process. And terminated, finished execution. The OS manages the transitions between these states.
And the process scheduler decides who goes from ready to running.
Exactly. The scheduler is a key part of process management. In a system with multiple processes ready to run, the scheduler uses an algorithm to select which one gets the CPU next, and potentially for how long, it's time slice or quantum and time sharing. This constant switching between processes is what gives us multitasking.
What kinds of scheduling algorithms are there? Is one always better?
There are many. Simple ones like first come, first served, FCFS. Shortest job, next, SJN, tries to minimize average waiting time, but needs to know how long jobs will run. Round robin gives each process a small, fixed time slice, ensuring responsiveness very common in interactive systems. Priority-based scheduling gives preference to more important processes. There's no single best algorithm. The choice depends on the system's goals, maximizing throughput, minimizing response time, meeting real-time deadlines, fairness, etc. Modern OS often use complex hybrid algorithms.
And switching between processes involves something called context switching.
Yes. When the scheduler decides to stop running process A and start running process B, the OS must perform a context switch. This involves saving the complete execution state of process A, its program counter, CPU register values, memory management info, etc., into a data structure called its process control block, PCB. Then the OS loads the save state of process B from its PCB into the CPU registers. Only then can process B resume execution from where it left off.
That sounds like it takes a bit of time itself.
It does. It's pure overhead. The CPU isn't executing application code during the switch. So OS designers try to make context switches as fast as possible, but they are an unavoidable cost of multitasking.
Okay, so process management is about creating, running, switching, and terminating programs. What about managing all the files on our hard drives? That's the file system management component.
Correct. This part of the OS is responsible for organizing and managing data on persistent storage devices like hard drives, SSDs, or USB drives. It allows us to store information in files, which are collections of related data, and organize those files into directories or folders.
It gives us that hierarchical structure we're used to, folders within folders.
Exactly. The file system manager handles creating files and directories, deleting them, reading data from files, writing data to files. It also manages file attributes, things like the file name, size, type, creation, modification, timestamps, and importantly, access permissions, who can read, write, or execute the file.
And it deals with the physical disk, too.
Yes. Underneath the logical structure of files and directories, the file system manager has to keep track of where the data blocks corresponding to each file are physically located on the storage medium. It also handles things like ensuring data integrity, maybe managing disk space allocation, and providing the mechanisms for accessing file data. We encounter different file systems with different features. Windows commonly uses NTFS. macOS uses HFS Plus or the newer APFS. Linux uses various systems like XT4, XFS, or BTRFs. The choice impacts performance, reliability features like journaling to prevent data loss after a crash, security options, and file size limits.
How does the OS talk to all the different physical devices connected? Printers, keyboards, network cards, graphics cards.
That's the job of device drivers and the I/O manager. A device driver is a specialized piece of software, often written by the hardware manufacturer, that acts as a translator between the OS and a specific piece of hardware.
So the main OS doesn't need to know the intimate details of every single graphics card model out there.
Exactly. The OS knows how to talk to a generic graphics driver interface. The specific driver for your graphics card then translates those generic OS requests, like draw this rectangle, into the low-level commands that that particular piece of hardware understands. This modular approach is crucial. You can add new hardware to your system simply by installing the appropriate driver. The OS kernel loads and manages these drivers. There can be different types, like function drivers that directly control the device, and filter drivers that modify I/O requests. The I/O manager is a part of the OS kernel that handles all input-output requests from processes or other parts of the kernel. It routes requests to the correct device driver, manages data buffers, schedules I/O operations, since devices are often much slower than the CPU, and tries to ensure reliable, error-free communication. It provides a consistent interface for the rest of the OS to interact with devices, hiding much of the hardware complexity.
And you mentioned hardware abstraction layers, HALs, before. Where do they fit in this I/O picture?
HALs sit at a very low level, providing a standardized interface between the main OS kernel components, like the memory manager or process scheduler, and the core platform hardware, like the specific motherboard chipset, interrupt controller, timers, or CPU architecture variations.
So it hides hardware differences from the kernel, while drivers hide device differences from the OS.
That's a good way to think about it.
Yeah.
The HAL allows the bulk of the OS kernel code to be written in a more hardware-independent way. For example, the kernel might need to disable interrupts. It calls a standard HAL function like HAL disable interrupts. The specific HAL implementation for the current hardware platform then executes the necessary machine instructions to actually disable interrupts on that specific interrupt controller. This makes porting the OS to different hardware architectures much easier. You primarily need to adapt or rewrite the HAL rather than changing code scattered throughout the kernel. Device drivers then often interact with the HAL or standardized interfaces provided by the I/O manager that sit above the HAL.
Okay, that makes sense. And finally, the part we actually see and interact with, the user interface, UI.
Right. This is the layer that allows humans to communicate with the OS and launch control applications. The most common type today is the graphical user interface, GUI, using windows, icons, menus, pointers, mice, touchpads, etc. Think Windows Desktop, macOS Finder, smartphone interfaces. But there's also the command line interface, CLI, which is text-based. Users type commands directly into a terminal or console. Examples include Bash or Zoosh on Linux, macOS, or PowerShell and Command Prompt on Windows. Some systems offer both, and many power users or system administrators rely heavily on the CLI for its efficiency and scripting capabilities.
Thinking about building all these incredibly complex pieces, the kernel, managers, drivers, UI, what programming languages are typically used? It can't all be super high level, can it?
No, especially not for the performance-critical parts. The kernel itself, core memory management, schedulers, and often device drivers are typically written in C, and sometimes even bits of assembly language.
Oh, I see.
C provides the necessary low-level control over memory addresses and hardware registers, which is essential for interacting directly with the hardware. It compiles to efficient machine code, but it still offers structured programming features that make managing complex code bases more feasible than pure assembly. It's been the dominant language for systems programming for decades.
But not everything. What about the UI or utilities?
Higher-level components often use higher-level languages. C++ is common for performance-sensitive applications or parts of the OS that benefit from object-oriented features. User interfaces might be built using frameworks that rely on Objective-C or Swift, macOS, C# or C++ Windows, or various languages including Python, or using toolkits like GTK-Qt on Linux. There's a constant trade-off between performance, developer productivity, and safety. Recently, there's been growing interest in using languages like Rust for systems programming, including parts of kernels like Linux or writing drivers. Rust's strong focus on memory safety, preventing common errors like buffer overflows or use after free bugs at compile time, is very attractive for building more secure and reliable OS components.
So a mix of languages, choosing the right tool for the specific job within the OS.
Exactly. Low level for the core, higher level where productivity and abstraction are more important.
Okay, we have the anatomy now. Kernel, Memory management, process management, file system, I/O, and drivers, UI. How do they all dance together? Let's walk through a simple common task. Say, I double-click a document file on my desktop. What happens inside the OS?
Okay, good example. It involves many of these components working in sequence. It's a continuous cycle orchestrated by the kernel. 1. User interaction. You double-click the document icon using your mouse. The GUI shell, like Windows Explorer or Mac OS Finder, registers this mouse event. 2. UI to OS translation. The GUI shell identifies the file you clicked on. It knows, probably from the file extension or metadata, which application is registered to open this type of document. Example, a word processor for a .docs file. It needs to tell the OS to launch that application and pass it the document file as an argument. 3. System call FS. Launching an application and opening a file require kernel services. The GUI shell will make one or more system calls. First, likely a system call to create a new process for the word processor application if it's not already running. This involves requesting memory allocation, loading the application's code, etc. Then, potentially another system call from the now running application process to open the specific document file you clicked on.
So the application asks the kernel to open the file for it.
Yes. Applications running in user mode cannot directly access files or hardware. They must go through the kernel via system calls for these privileged operations. This is a fundamental security principle. 4. Mode transition. Each system call triggers a mode transition. The CPU switches from user mode to the privileged kernel mode. The system call usually includes an identifier for the requested service, for example, create process or open file, and any necessary parameters, like the program name with a file path. 5. Kernel processing. Process creation. If launching the app, the kernel system call handler directs the request to the process manager. It allocates resources. The PCB, memory space via the memory manager, potentially loads the application's executable code from disk using the file system and I/O managers. 6. Kernel processing. File open. When the application makes the open file system call, the kernel directs this to the file system manager. It checks the file path, verifies the application has the necessary permissions to access that file using the security information stored with the file. If permissions are okay, it locates the file's metadata on the storage device. 7. Kernel processing. I/O. The file system manager interacts with the I/O manager and the appropriate storage device driver to read the file's metadata. And eventually, the file's data blocks from the physical disk or SSD into memory buffers. 8. Interrupt handling. As the disk read operations happen, the storage device controller will likely use interrupts to signal the CPU when data blocks are ready or the operation is complete. The kernel's interrupt handlers process these signals, perhaps waking up the application process if it was waiting for the data. 9. Completion and return to user mode. Once the kernel service, process creation or file open, is complete, the kernel prepares any results, like a file handle for the open file or just a successor of code. It then transitions the CPU back to user mode, returning control to the application process along with the results. 10. Application processing and output. The application, the word processor, now has the file open. It reads the data from the file via further system calls, processes it, and then makes more system calls to the OS, specifically to the graphics subsystem via its driver, to draw the document's content inside its window on the screen for you to see.
Wow, okay, so even a simple double-click triggers this incredibly complex cascade of events. UI interpretation, multiple system calls, mode switches, coordination between process management, memory management, file system, I/O, drivers, interrupt handling, all just to open a document.
Exactly. It's this constant, intricate choreography managed by the OS kernel, juggling resources, enforcing security, and interacting with hardware that makes the whole system function and appear relatively seamless to the user. It's a nonstop balancing act.
Before any of that can happen, though, the OS itself needs to get loaded and running when you first turn the computer on. What are the absolute essential prerequisites for an OS to even boot up?
Right, the OS doesn't just magically appear. There's a critical startup sequence that relies on several foundational pieces being in place. 1. Basic hardware. Obviously, you need functional core hardware. A compatible CPU, enough RAM to hold the initial kernel and boot processes, a storage device like an SSD or hard drive where the OS is actually installed, a motherboard connecting everything, and usually some basic I/O like a display controller. 2. Firmware, BIOS CFI. This is low-level software stored on a chip on the motherboard. When you press the power button, the firmware is the very first thing that runs. It performs a power-on self-test, PACE test, to check that the basic hardware components are present and working. Its main job after PST is to find and load the next piece of the puzzle, the bootloader.
So the firmware kicks things off and hands over to the bootloader.
Exactly. The bootloader is a small program located in a specific, well-known place on the storage device, like the master boot record, MBR, on older systems, or an EFI partition on newer UEFI systems. The firmware finds this bootloader, loads it into RAM, and executes it. The bootloader's sole purpose is then to load the main operating system kernel file, or core kernel components, from the storage device into RAM, and then transfer control to the kernel, essentially telling it, okay, you're in charge now.
So power firmware PC deck bootloader deck your kernel -S takes over.
That's the fundamental boot sequence. Newer systems with UEFI firmware often include features like Secure Boot, where the firmware verifies digital signatures on the bootloader and the kernel before loading them to prevent malicious software from hijacking the boot process. 3. Essential software components. The OS kernel, once loaded, needs immediate access to at least some basic device drivers, particularly the driver for the storage device it was loaded from, and likely a display driver to show output. It might also rely on some very fundamental platform libraries for its initial setup. So it's this careful chain. Working hardware allows the firmware to load the bootloader, which loads the kernel, which then uses basic drivers to initialize the rest of the system. If any link in that chain is broken, the system won't boot.
Security is obviously paramount in modern systems. We've touched on memory protection and secure boot. What other fundamental ways does the OS safeguard the system and user data?
Security is woven into many layers of the OS. Beyond memory isolation, key mechanisms include 1. User authentication. This is the front door. The OS needs to verify a user's identity before granting any access. This is typically done with usernames and passwords, but increasingly involves biometrics, fingerprint, face recognition, or multi-factor authentication, MFA. Once authenticated, the user operates under a specific user ID, UID, or security identifier, SID. 2. Access control models. Just because you're authenticated doesn't mean you can do anything. Access control determines what an authenticated user is allowed to do with specific resources, files, devices, etc. The sources mention several models. Access control lists, ACLs. These are lists attached directly to objects, like files or folders. The ACL specifies exactly which users or groups have what kind of permissions. Virtually Alice can read, Bob can read, write, administrators have full control. Very granular. Role-based access control, RBAC. Common in enterprise environments. Permissions are associated with defined roles like accountant, developer, backup operator, and users are assigned to one or more roles. This simplifies managing permissions for large numbers of users. Mandatory access control, MAC. A stricter model often used in high-security systems, like military or intelligence. Access decisions are based on system-wide security labels assigned to both users, subjects, and resources, objects. The OS enforces these policies rigidly, and users typically cannot change permissions themselves. So Linux is an example. Discretionary access control, DAC. This is the most common model on systems like Windows and Linux for files. The owner of a resource, or the user who created a file, has the discretion to grant or deny access permissions to others. Standard file permissions, read, write, execute for owner group others, are a form of D. 3. Kernel enforcement. The kernel is the ultimate enforcer of security policy. User versus kernel mode. We keep coming back to this because it's fundamental. The strict separation ensures that potentially buggy or malicious user applications cannot directly access critical hardware or interfere with the core OS functions running in the privileged kernel node. System calls are the controlled, validated gates between these modes.
The kernel acts as the gatekeeper.
Exactly. A critical security boundary. Process isolation. As discussed with memory management, ensuring processes run in their own protected memory spaces prevents them from interfering with each other. Resource protection. The OS must protect system resources, like the CPU, preventing one process from monopolizing it, often using timer interrupts, I/O devices, ensuring only authorized processes can access them, and kernel data structures. Security policies. The OS implements and enforces broader system policies, things like minimum password length, how often passwords must be changed, account lockout after failed login attempts, rules for auditing, maybe enforcing data encryption on disk. 4. Auditing and logging. Modern OCs typically maintain detailed logs of significant system events, user logins, logouts, file access attempts, successes and failures, administrative actions, system errors, etc. These logs are crucial for security monitoring, detecting suspicious activity, investigating security incidents after they occur, forensics, and demonstrating compliance. So it's a layered defense strategy aiming to protect the system's integrity, the confidentiality of data, and ensure the availability of services. How well an OS implements these security features is a major factor in its overall quality.
That provides a really thorough picture of the complex machinery inside a modern OS, how it functions, and how it protects itself. It's certainly come a long way from those early monitors. We're going to take a short break, and when we return, we'll discuss how we evaluate these complex systems, what makes one OS better than another, and we'll look at Windows and Linux as case studies. Just a quick reminder, if you're finding this deep dive informative, hitting that subscribe button and following the channel really helps us out. And please, if questions pop into your head, add them to the comments. We're keen to discuss them. We find these topics genuinely exciting.
Evaluating operating systems, measures of quality.
Welcome back to the deep dive on operating systems. We've dissected the anatomy of a modern OS. Now let's tackle the tricky question. How do we evaluate them? What makes an OS good or bad? It seems subjective sometimes.
It can feel that way, but there are definitely key quality attributes we can use as yardsticks. As the sources point out, judging an OS isn't just about one thing. It's multidimensional, and crucially, there are often trade-offs. Improving one aspect might compromise another. These qualities are sometimes called non-functional requirements. They describe how well the system works, rather than just what functions it performs.
Okay, so what are the main quality attributes our sources highlight? What should we look for?
1. Stability and reliability. This is often number one for users. Does the OS run consistently without crashing? Does it behave predictably? A reliable OS has few failures, and when problems do occur, it handles them gracefully, maybe recovering automatically, fault tolerance, or allowing data and system state to be restored, recoverability. This depends heavily on solid memory management, good error handling throughout the system, and resolving resource conflicts fairly. Think about real-time operating systems, RTOS, used in critical applications like medical devices, flight control systems, or industrial automation. For them, predictability and reliability, meeting strict timing deadlines, are the absolute highest priorities, often above all else. User trust really depends on stability. 2. Security and robustness. We've talked a lot about security mechanisms. A high-quality OS must effectively protect itself and user data from threats, unauthorized access, malware, data breaches. It needs to ensure data integrity, preventing unauthorized modification, and data confidentiality, preventing unauthorized disclosure. This requires robust authentication, strong access controls, maybe built-in encryption features. Robustness is related. It's about how well the OS handles errors, unexpected inputs, or stressful conditions like running out of memory without feeling completely or becoming insecure. 3. Efficiency and performance. This is about how well the OS uses the available hardware resources, CPU time, RAM, I/O bandwidth. Does it feel responsive? Do applications launch quickly? Does it complete tasks efficiently with minimal overhead from the OS itself? Good performance also includes scalability, how well the OS handles increasing workloads or more hardware, like extra CPU cores. This comes down to efficient scheduling algorithms, optimized memory management, fast I/O handling, and minimizing the OS's own footprint. 4. Usability and user experience, UX. How easy and pleasant is the OS to interact with? This includes an intuitive design, a clear and consistent user interface, whether GUI or CLI, good documentation or help systems, and accessibility features for users with disabilities or different skill levels. The UI is the bridge between the user and the system's power, so its quality significantly impacts productivity and satisfaction.
And you mentioned trade-offs between these.
Absolutely. It's a constant balancing act. For example, implementing very strict security measures might introduce extra checks and overhead, potentially slowing down performance slightly. A highly optimized, high-performance kernel might be more complex and harder to debug, potentially impacting stability initially. A super simple, easy-to-use interface might hide advanced options that power users need.
So the best OS really depends on the context.
Precisely. The ideal balance of these attributes depends entirely on what the OS is intended for. An OS for a life support machine has vastly different priorities than a desktop OS for gaming, which is different again from an OS running a massive web server farm or one designed for a tiny IoT sensor.
Let's make this concrete with the case studies from the sources. First up, Windows. Undeniably dominant on desktops and laptops. How does it stack up against these attributes?
Windows is widely recognized for its usability and polished GUI. It's generally considered user-friendly, especially for people familiar with the Microsoft ecosystem. A huge strength is its vast software and hardware compatibility. Because of its market share, most software is written for Windows, and hardware manufacturers prioritize providing Windows drivers. It integrates well with Microsoft's other products and services.
What about the potential downsides mentioned? Complexity and resource use.
Yes, the sources suggest that this user-friendly surface can sometimes mask significant underlying complexity. Windows often runs numerous background services, which can make it relatively resource-heavy compared to some leaner alternatives, particularly some Linux distributions. This means it might feel sluggish on older or lower-spec hardware. Historically, it also had a reputation for needing frequent security patches, although Microsoft has invested heavily in improving its security posture with features like Windows Defender and a robust update process.
Where does it excel in performance?
It's generally well optimized for common consumer and business tasks, multimedia playback, gaming, thanks to DirectX and strong driver support from graphics card vendors, and running popular productivity suites like Microsoft Office. It tries to balance interactive responsiveness for the user in the foreground with managing those background tasks. But this can sometimes lead to higher idle resource consumption compared to systems designed for pure efficiency.
Okay, now let's contrast that with Linux, primarily known in server rooms and among developers, but with various desktop versions too. How does it differ in terms of these quality attributes?
Linux is fundamentally different because it's an open source kernel, forming the basis for hundreds of different distributions, like Ubuntu, Fedora, Debian, Arch. Its defining characteristic related to quality is often its flexibility and customization.
And that leads to efficiency.
Often, yes. Because it's open source, users or administrators can modify and tune the system extensively. You can strip out unneeded components, recompile the kernel with specific optimizations, and configure services precisely for the intended workload. This makes Linux highly efficient in resource utilization. It can be configured to have minimal overhead, which is why it dominates servers, embedded systems, supercomputers environments, where maximizing hardware potential is critical. It can also often run very well on older or less powerful hardware where Windows might struggle.
The power of tuning. What's the trade-off often cited for Linux, especially for typical desktop users?
Historically, it's been usability and the learning curve. While some distributions like Ubuntu or Mint offer very polished, user-friendly desktop GUIs that rival Windows or macOS, many others offer more control but require more technical knowledge, often involving use of the command line terminal. For users accustomed only to GUIs, mastering Linux can be more challenging, although the situation has improved dramatically over the years. The sheer diversity of distributions in desktop environments can also be confusing for newcomers.
So the comparison really highlights different philosophies. Windows aiming for broad consumer ease of use, massive compatibility, and integration within its ecosystem. Linux prioritizing openness, flexibility, efficiency, and control, making it ideal for technical users, servers, and customized solutions.
Exactly. Neither is universally better. Their strengths and weaknesses reflect these different design goals and target audiences. The best choice depends entirely on the user's needs, technical skill, and the specific application.
A critical factor for any OS's success is hardware compatibility. How do modern OCs manage to work with the thousands of different hardware components out there? It seems like a nightmare.
It's a huge challenge, but they rely on several key architectural principles and mechanisms. 1. Modular device drivers. This is the cornerstone. As we discussed, drivers are the translators. The modularity means the core OS doesn't need to know about every specific device. When new hardware comes out, the manufacturer provides a driver and users install it. The OS just needs a standard way to load and communicate with these driver modules. 2. Hardware abstraction layers, HALs. Again, the HAL provides that standardized interface below the main kernel, hiding variations in core platform hardware, motherboards, chipsets, etc. This allows the OS kernel itself to be more portable across different underlying hardware architectures. The kernel talks to the HAL talks to the specific platform hardware.
So drivers handle specific devices, HALs handle specific platforms.
That's a good simplification, yes. It creates layers of abstraction. 3. Standardized interfaces and APIs. Things like the POC at standard define common ways for applications to request OS services, file I/O, process creation, networking. OCs that adhere to these standards, like Linux, macOS, BSD, make it easier for developers to write applications that can run on different systems with minimal changes. This promotes software compatibility across compliant OCs. 4. Plug-and-play PnP technologies. Most modern OCs have sophisticated PnP systems. When you connect a new device, like a USB drive or a printer, the OS automatically detects it, queries the device for identification information, tries to find and load the appropriate driver, either one built-in, previously installed, or perhaps prompting the user or downloading it, and configures the necessary system resources like interrupt lines or memory addresses for the device to work. Managing hardware compatibility is a continuous massive effort for OS vendors. New devices appear constantly, but these mechanisms, modular drivers, abstraction layers like HAL, standardized APIs, and PnP are the essential tools they use to manage this complexity, decouple the OS from specific hardware, foster broad support, and allow the ecosystem to adapt. Without them, you'd essentially need a custom-built OS for every slightly different hardware configuration, which would be completely impractical.
Let's talk about another practical aspect users experience, patching and updates. How do Windows and Linux compare in how they handle keeping the system up to date and secure? Their approaches seem quite different.
They were very different, largely reflecting their development models, proprietary versus open source, and target audiences. Let's look at Windows Update first. Centralized delivery. Microsoft controls and delivers virtually all updates for the Windows OS itself, security patches, bug fixes, feature updates, and often drivers for common hardware through the Windows Update service. It's a single source. Automated process. By default, Windows Update is highly automated. It checks for, downloads, and installs updates in the background, often requiring scheduled or sometimes forced reboots to apply them. The goal is to keep systems updated with minimal user intervention, which is good for less technical users. Potential disruptions. This automation, especially the mandatory reboots or lengthy update installations, can sometimes be perceived by users as disruptive to their workflow. Closed source. Because Windows is proprietary, users are entirely dependent on Microsoft to identify vulnerabilities and release patches. The source code isn't public, so the wider community can't inspect it for flaws or develop independent patches. However, Microsoft has extensive internal security teams and processes for this.
Now, compare that to Linux updates. Decentralized and varied, the Linux kernel itself is updated by a global community of developers. Updates for all of the other software that makes up a Linux distribution, the desktop environment, utilities, applications, are managed by the maintainers of that specific distribution, URI, Canonical for Ubuntu, Red Hat for RHEL, the Debian project, etc. Distribution-specific tools. Each distribution uses its own package manager, like apt on Debian Ubuntu, dnfio on Fedorio, pacman on Arch. These tools handle finding, installing, updating, and removing software packages from configured repositories, servers holding the software. User control. Generally, Linux users have much more granular control over the update process. They can typically choose which updates to install and when to install them. While security updates are strongly recommended, forced reboots are rare for most package updates, though kernel updates usually require a manual reboot to take effect. Open source advantage. The transparency of open source is often seen as a security benefit. Anyone can inspect the source code for vulnerabilities, and the community can often identify and develop patches very quickly. Potential complexity. This flexibility comes with potential complexity. Managing software sources, repositories, dependencies between packages, and ensuring compatibility across a distribution can sometimes be challenging, especially for new users or in large, diverse environments. There's also the responsibility on the user admin to actually apply the updates. Using distributions or versions that are end-of-life, EOL, and no longer receiving security updates, like old CentOS versions, is a significant security risk.
So it sounds like Windows offers a more managed, automated, one-size-fits-all update experience, convenient, consistent, but less control and transparency. Linux offers a more distributed, flexible, open model with high user control and potential for rapid community response, but requires more user knowledge and careful management.
That captures the core difference as well. The better approach really depends on the user's technical expertise, the environment, for example, single home PC versus large server fleet, and whether they prioritize convenience or control.
This gives us a really solid framework for thinking about OS quality and the practical differences between major systems. We understand the past and the present. Now let's gaze into the crystal ball. Where is the world of operating systems heading next?
The future looks dynamic, to say the least. It's being shaped by powerful forces like the cloud, artificial intelligence, new security threats, the need for sustainability, and even potentially disruptive hardware like quantum computers.
Sounds like a lot of change on the horizon. Before we dive into that future, one last reminder for everyone listening. If you're finding this exploration valuable, please do hit subscribe and follow Silent Mind Studio. It makes a big difference. And if you have questions brewing or thoughts to share, the comments section is the place. Engaging with you is genuinely exciting for us.
The Horizon Future Trends and Challenges.
Welcome back to the Deep Dive. We've journeyed from the vacuum tubes and punch cards that marked the birth of operating systems through their evolution, dissected their modern anatomy, and discussed how we evaluate them. Now, let's look forward. What are the key trends shaping the future of OS development, according to our sources?
The landscape is definitely evolving, driven by relentless technological change and shifting user needs. Several major directions emerge from the material we have. First, deepening cloud integration and the idea of OS as a service, OSAS. The traditional model of an OS managing just one physical machine is becoming less central for many applications. OS functionality is increasingly delivered, managed, or abstracted away by cloud platforms.
How does that work in practice, like with infrastructure as a service?
In IANs like Amazon EC2 or Azure Virtual Machines, the cloud provider manages the physical hardware and a crucial layer called the hypervisor. The hypervisor is essentially a specialized low-level OS whose job is to create and manage virtual machines, VMs. As a user, you then deploy and manage your own chosen guest OS, like Windows Server or Linux distro, inside that VM. So the cloud provider runs the underlying OS hypervisor, and you run an OS on top of that.
What about platform as a service?
PALAS goes a step further in abstraction. With something like Google App Engine or Heroku, the cloud provider manages the underlying infrastructure, the operating systems, middleware, everything. Developers just deploy their application code, and the platform handles the rest. The OS becomes almost invisible to the developer. And then you have containers as a service, CaaS. Platforms like Kubernetes manage the deployment and scaling of containers, like Docker. Containers use OS-level virtualization. They share the host machine's OS kernel, but run in isolated user spaces. So the OS is still there, the host OS, but CaaS provides an abstraction layer for managing containerized applications that feels somewhat like an OS interface itself.
So the OS is still present, but its role and visibility are changing dramatically depending on the cloud model.
Exactly. It's shifting from being solely a single machine manager to being part of a distributed system, or an abstracted layer, or the foundation upon which these cloud services are built. This allows for incredible resource pooling, scalability, and on-demand provisioning. And research is pushing this further. The sources mention AI-enhanced cloud OS. Concepts like OSML+ use machine learning to optimize scheduling of services running together in the cloud. There's even the vision of FM4OS using large AI foundation models to potentially replace traditional OS heuristics for making smarter, more adaptive decisions about resource management in hugely complex cloud environments.
That's a perfect segue to the second major trend, the rise of AI-driven OS more broadly.
Yes, AI is expected to fundamentally transform operating systems, making them more intelligent, proactive, predictive, and adaptive.
How could AI improve those core OS functions we discussed, like scheduling or memory management?
The idea is that AI, particularly machine learning, can learn complex patterns in system behavior and application workloads far better than predefined static rules or heuristics used in traditional OS design. An AI-powered scheduler could learn the specific needs of different applications and dynamically adjust CPU allocation for optimal performance or energy efficiency in real time. An AI memory manager could predict which data pages are likely to be needed soon and proactively fetch them, or optimize swapping decisions based on learned access patterns. We saw the examples OSML+ and FM4OS in the cloud context, but the principle applies more broadly, potentially significant gains in efficiency and performance.
What about the user experience? How might AI change how we interact with the OS?
One major area is natural language interfaces, NLI. Using powerful language models like those behind ChatGPT, you could potentially interact with your OS using plain English commands. Imagine telling your computer, find all photos from my trip to Italy last summer and create a shared album. And the OS understands the intent and executes the necessary file searches, application launches, and sharing actions.
Just talking to your computer, that would be a massive shift.
It would be. Early projects like NL2SH, translating natural language to shell commands, show the potential. Of course, there are huge challenges in accurately understanding ambiguous human language, ensuring the correct actions are taken, and doing it securely. AI could also enable highly personalized and adaptive user experiences, learning your preferences, work habits, and context to proactively offer relevant information, shortcuts, or system configuration adjustments, potentially across different devices.
And security. Can AI bolster OS defenses?
That's a key area of focus. AI can be integrated into security tools for much more sophisticated threat detection. AI algorithms are good at spotting anomalies and subtle patterns in system activity or network traffic that might indicate a novel attack missed by traditional signature-based antivirus. AI can analyze program behavior to identify malware, like the MS Android example using deep learning on Android app behaviors, and potentially automate responses to security incidents much faster than humans can react. This is seen as crucial for dealing with increasingly sophisticated cyber threats. But, as the sources warn, integrating AI deeply into the OS isn't without challenges. It adds significant complexity. Running large AI models efficiently at the OS level is difficult, and as we started to discuss, there are critical ethical considerations.
Let's revisit those ethical concerns because they seem really important as AI gets closer to the core of the system. The sources mentioned bias. How could an OS become biased?
It's a serious risk. AI models learn from data. If the data used to train the AI components within an OS reflects existing societal biases, the OS itself can perpetuate or even amplify those biases in its decision-making. For example, an AI resource scheduler, trained on biased data, might learn to unfairly deprioritize tasks, typically run by certain user groups. An AI-powered natural language interface might understand certain accents or dialects much better than others, creating usability barriers. Security systems using AI pattern recognition could potentially learn to associate innocuous behaviors with threats if the training data is skewed, leading to discriminatory outcomes like disproportionately flagging certain individuals or groups. Embedding bias at such a fundamental system level could have really widespread negative consequences.
And privacy. An AI OS sounds like it would need a lot of data about me.
That's the concern. To personalize your experience or optimize performance based on your usage, an AI-driven OS might collect and analyze vast amounts of data about how you use your device, what applications you run, maybe even your communication patterns or biometric data. This raises huge questions about informed consent for data collection, how securely that data is stored, who it might be shared with, and the potential for creating incredibly detailed user profiles that could be misused. What data is essential and what crosses the line?
That's a line that seems easy to cross. What about accountability and transparency? If an AI OS makes a mistake, who's responsible?
That's the black box problem. Many advanced AI models are incredibly complex, and even their creators don't always fully understand why they arrive at a specific decision. If an AI component in the OS makes a flawed decision, maybe it incorrectly flags a legitimate program as malware, or misallocates resources causing a system failure. Debugging the issue can be extremely difficult. Assigning responsibility becomes murky. This lack of transparency can erode user trust. How can you trust a system when you don't understand how it makes critical decisions?
So how do we address these ethical challenges? What do the sources suggest?
It requires a conscious, multi-pronged effort throughout the design and deployment lifecycle, adhering to ethical frameworks, explicitly incorporating principles like fairness, transparency, accountability, and non-maleficence into the OS design process, guided by standards from organizations like IEE or ACM, bias detection and mitigation, actively working to identify and reduce bias in training data and AI models using techniques like diverse data sourcing, algorithmic fairness checks, and regular audits, privacy by design, building privacy protections in from the outset, not as an afterthought. This includes minimizing data collection, using anonymization or differential privacy techniques, and ensuring strong data encryption and security. Transparency and explainability, XAI. Researching and implementing techniques that make AI decisions more understandable to developers and potentially even end users. Auditing and monitoring. Continuously monitoring AI components in the OS for performance, fairness, and unexpected behavior after deployment. Cross-disciplinary collaboration, involving not just engineers but also ethicists, social scientists, legal experts, and diverse user representatives in the development process. The sources emphasize that building ethical AI-driven OS is not just a technical problem, but a societal necessity. Failure risks real harm, erode public trust, and can hinder the adoption of potentially beneficial AI advancements.
It adds a whole new layer of complexity to OS design. Moving back to security threats, what are the next big challenges OS developers need to prepare for?
The threat landscape never stands still. 3 major areas stand out. 1, AI-powered cyber attacks. Just as defenders are using AI, attackers are too. We're seeing AI used to create much more convincing phishing emails, automate reconnaissance, generate polymorphic malware that constantly changes its signature to evade detection, and even launch adversarial attacks specifically designed to fool AI-based security systems. OS defenses will need to become equally sophisticated and AI-driven just to keep pace. It's becoming an arms race. 2, IoT security. The sheer number of Internet of Things devices, smart speakers, cameras, sensors, appliances is exploding. Many of these devices have minimal processing power, limited memory, and often weak or non-existent security features, creating a massive new attack surface. Compromised IoT devices could be used in botnets for large-scale attacks like DDoS. Operating systems designed for IoT devices or for the gateways that manage them need to be extremely lightweight, but also incorporate robust security from the ground up. Secure boot, encrypted communications, secure update mechanisms, network segmentation. 3, quantum threats. This is a longer-term but potentially existential threat. Once large-scale, fault-tolerant quantum computers become available,
They will be able to break most of the public key cryptography algorithms, like RSA and ECC, that currently protect secure communication, HTTPS, data encryption, and digital signatures worldwide.
So all our current encryption could become useless.
Potentially, yes, for public key crypto. This means future operating systems will need to transition to using quantum-resistant cryptography, also called post-quantum cryptography, new algorithms believed to be secure against attacks by both classical and quantum computers. This needs to be integrated into everything from the OS's secure boot process and file system encryption to network protocols like TLS-SSL and user authentication mechanisms. It's a major cryptographic transition that needs to start happening now. The overall trend in OS security is moving towards more dynamic, adaptive defenses, embracing concepts like zero trust, never trust, always verify, and heavily leveraging AML for threat intelligence and response. Constant vigilance and adaptation are paramount.
Alongside security, there's that growing push for sustainability and energy-efficient OS. And how can the OS itself contribute to green IT?
The OS is uniquely positioned because it manages both hardware resources and software execution. It can play a significant role in reducing energy consumption, which is critical for data centers burning megawatts of power, but also just for extending battery life on your laptop or phone.
What specific strategies can the OS employ?
Several things. Power-aware resource management. The OS scheduler can try to consolidate workloads onto fewer CPU cores, allowing inactive cores to enter deep sleep states. It can manage memory power states too. Dynamic power management, DPM. This involves the OS actively monitoring the system workload and adjusting hardware power states on the fly. A key technique here is dynamic voltage and frequency scaling, DVFS, where the OS reduces the CPU's clock speed and voltage when the load is low, saving significant power, and ramps it up only when needed. It can also power down idle devices or peripherals. Optimized device drivers. Well-written drivers can intelligently manage the power states of the hardware they control, for example, putting a Wi-Fi chip into a low-power sleep mode when inactive. Support for energy-efficient hardware. The OS needs to be aware of and leverage specific power-saving features built into modern CPUs, chipsets, and other components.
While not strictly an OS feature, OS support for virtualization allows data centers to consolidate many virtual machines onto fewer physical servers, dramatically improving hardware utilization and reducing the total number of active and power-consuming servers. Carbon-aware scheduling. This is a fascinating new area. The idea is for the OS or workload manager, especially in data centers, to schedule computationally intensive but non-urgent tasks to run during times when the electricity grid has a higher proportion of renewable energy sources available or when the carbon intensity of generation is lower, shifting workloads in time or even geographically to minimize the carbon footprint. Software optimizations. While the OS can't force applications to be efficient, it can provide tools and libraries that help developers write more energy-aware code. And optimizing the OS's own code paths is important too. Even optimizing AI models, like using quantization, can reduce their energy footprint when running.
AI itself can also be used to optimize energy consumption, for example, by intelligently managing cooling in data centers or refining the OS's own power management policies. The key takeaway is that designing for energy efficiency is no longer a niche concern. It's becoming a mainstream requirement for OS development, impacting everything from low-level hardware interactions to high-level workload management.
Now for the really futuristic stuff, quantum computing. If we get working quantum computers, will they need their own specialized OS? How would a quantum OS even work?
That's a huge research question. Quantum computers operate on entirely different principles, superposition, entanglement, and have the potential to solve certain types of problems that are completely intractable for classical computers. Managing these systems will require radically new OS approaches or major adaptations.
What makes managing qubits so different from managing classical bits?
The sources highlight several unique challenges for a potential quantum OS, QoS. Qubit management. Qubits are incredibly fragile. They lose their quantum state decoherence very easily due to environmental noise, heat, vibration, electromagnetic fields. A QoS needs to manage the allocation, initialization, and measurement of these delicate qubits, which is far more complex than just flipping bits on or off. Error correction mitigation. Quantum computations are inherently noisy and error-prone. Implementing effective quantum error correction is extremely challenging and requires significant overhead, many physical qubits to represent one logical error-corrected qubit. A QoS would play a vital role in implementing error mitigation strategies and managing fault tolerance, hardware heterogeneity, and instability. Current and near-term quantum processors, QPUs, are diverse, experimental, and their performance, for example, qubit coherence times, gate fidelities, can vary significantly and even change over time. A QoS needs to abstract away this heterogeneity and instability, potentially scheduling computations on the QPU best suited for the task at that moment. Resource utilization. Quantum computing resources are currently very scarce and expensive. A QoS needs to manage these resources efficiently, potentially enabling multi-programming, running multiple quantum tasks concurrently or interleaved, without degrading the fidelity of the delicate quantum states.
Is anyone actually building a QoS? What might it look like?
It's mostly in the research phase. The sources mention concepts from academic papers proposing potential architectures. One example suggests components like a kernel, a core execution unit for quantum tasks, an error mitigator, applying techniques to reduce noise, a fidelity estimator, predicting performance on different QPUs, a multi-programmer, managing co-location of jobs, and a scheduler, balancing load, considering fidelity, providing a hardware-agnostic API. However, the most likely near-term scenario is hybrid quantum classical systems. In this model, the quantum computer acts as a specialized accelerator for specific parts of a larger computation, while a classical computer handles the overall control flow, data preparation, and analysis of results. The OS challenge here is managing the complex interaction, data transfer, and synchronization between the classical and quantum components. Middleware and specific architectural patterns are being developed for this. Developing a full-blown standalone QoS is a long-term interdisciplinary challenge involving physics, computer science, and engineering. But many fundamental OS principles, resource management, abstraction, scheduling, fault tolerance will still apply, just adapted to the bizarre rules of the quantum realm.
Fascinating. Another critical trend addresses a societal issue: bridging the digital divide. How can OS design help people in low-resource settings get access to technology?
The digital divide is a real and persistent gap in access, often caused by lack of reliable internet, affordable devices, stable electricity, or digital literacy, especially in developing countries or underserved communities. OS and software design can make a difference here.
What are the specific constraints OS designers face in these environments?
The sources list quite a few.
Internet access might be slow, unreliable, expensive, or completely unavailable.
Users might have older, low-power smartphones or basic feature phones, or older desktop computers with limited RAM and CPU power.
The cost of devices and data plans can be prohibitive.
Users may have low general literacy or low digital literacy, making complex interfaces unusable.
Electricity supply might be intermittent or unavailable, making battery life critical.
Software interfaces are often only available in major world languages, creating barriers.
Many assumptions baked into mainstream OS design, like constant high-speed internet or powerful hardware, simply don't hold true.
So how do OS and software adapt?
It's often less about creating entirely new general-purpose OCs and more about adapting OS principles and building tailored software ecosystems. Lightweight design, optimizing the OS footprint and applications to use minimal CPU, RAM, and storage. This might involve using specialized Linux distributions or stripping down existing ones. Offline functionality, this is crucial, designing applications and systems that can function effectively without a constant internet connection. Data can be stored locally and synced later when connectivity is available. Examples mentioned include ODK for field data collection or Calibri for accessing educational content offline. Alternative communications, leveraging technologies that work over basic mobile networks like SMS or USSD, simple text-based menu systems, or even voice interfaces where data networks are poor. Examples like M-Pesa, mobile money via SMS, or Ushahidi, crisis mapping via SMSweb, show the power of this.
Using SMS for complex applications is really clever.
It leverages the most ubiquitous infrastructure available in many places. Simplified UIs. Designing interfaces that are extremely intuitive, using clear icons, visual aids, local languages, and potentially voice prompts, catering to users with low literacy or limited experience with technology. Low-cost open source. Utilizing open-source operating systems like Android variants or Linux and applications reduces licensing costs and allows for local customization and community support. Energy efficiency. Software must be designed to sip power, maximizing battery life on mobile devices or allowing operation with intermittent power sources. Systems like ComCare, mobile platform for frontline health workers, demonstrate how these principles can be combined effectively. The key is adapting technology to the constraints, applying OS concepts like efficiency and modularity within software stacks that have minimal OS footprints, ultimately making digital tools accessible and useful where they're needed most.
Let's talk about open source OS. Linux is already huge in servers and underlies Android. What does the future hold?
Will it take over the desktop too?
Open source, particularly Linux-based systems, is incredibly influential, and its role seems set to continue growing. The global market for open source services is projected to be massive. Linux absolutely dominates the server market, powers the vast majority of the world's supercomputers, and, as you said, is the foundation of Android, which dominates mobile.
What keeps driving this adoption, especially in enterprise?
Several key factors.
No licensing fees for the OS itself is a major draw, especially for large deployments. Flexibility and customization. Businesses can modify the source code, tailor the OS to their specific needs, integrate it with other systems, and avoid vendor lock-in. Innovation and community support. The collaborative open development model often leads to rapid innovation. There's a huge global community providing support, documentation, and expertise, security and transparency. The ability for anyone to inspect the source code is seen as a security advantage. Many eyes make all bugs shallow. Vulnerabilities can often be identified and patched quickly by the community.
In the enterprise, open source is foundational for modern trends like cloud computing — most cloud infrastructure runs on Linux — containerization, Docker, Kubernetes run primarily on Linux, AML and big data — most frameworks and tools are open source and run best on Linux, and edge computing AOT, where lightweight, customizable OSS is ideal. We're also seeing the rise of commercial open source models. Companies like Red Hat, SUSE, and Canonical build businesses by providing paid subscriptions for enterprise-grade support, certified hardware compatibility, management tools, and long-term maintenance for their Linux distributions, making OSS viable for risk-averse corporations.
What about the consumer desktop? Windows and Mac OS still seem dominant there.
They are, by a large margin, but user-friendly Linux distributions like Ubuntu, Mint, and Pop! OS are steadily gaining traction, particularly among developers, scientists, and tech-savvy users who value the flexibility or prefer the open-source philosophy. And Chrome OS, another Linux-based system, has carved out a significant niche in education and budget laptops. So while maybe not taking over the traditional desktop soon, open-source influence is definitely growing beyond servers and mobile.
Are there still challenges for open source OS?
Yes. Managing updates and dependencies across potentially thousands of open source packages can still be complex. Security requires diligence ensuring systems are actually patched, and avoiding EOL software is crucial. There can be a skills gap in finding personnel with expertise to manage and secure complex open source deployments, especially in newer areas. And as AI becomes more prevalent in open source, ensuring ethical development and preventing misuse of open source AI tools is an emerging concern. But overall, the future of operating systems is deeply intertwined with open source. Its strengths in cost, flexibility, and community innovation are driving its dominance in many critical infrastructure areas, and commercial support models are making it increasingly enterprise-ready.
This leads to a final, perhaps sobering point from the sources. Given the dominance of incumbents and all the challenges we've discussed, how hard is it to create a brand new general-purpose operating system from scratch today? Is it even feasible?
The sources are pretty unanimous. It is extraordinarily difficult, maybe even practically impossible for a general-purpose OS aiming for broad adoption. The barriers to entry are immense.
What are the biggest hurdles?
It's intense competition. You're going up against giants Microsoft, Apple, Google, and the entire Linux ecosystem who have decades of development, massive user bases, huge developer communities, vast resources, established distribution channels, and brand recognition. It's incredibly hard to displace that inertia. The ecosystem challenge, apps and developers, this is often considered the killer. An OS is useless without applications. But developers won't invest time and resources building apps for a new OS with few users, and users won't switch to a new OS if the apps they need aren't available. It's a vicious cycle, the classic chicken and egg problem. Building that critical mass of both users and developers simultaneously is incredibly difficult. Hardware driver support. A new OS needs drivers for an enormous, constantly changing range of hardware components: CPUs, GPUs, Wi-Fi chips, printers, webcams, everything. Convincing hundreds of hardware vendors to write and maintain high-quality drivers for your unproven OS is a monumental, often insurmountable task. Limited hardware support cripples usability, user adoption, and switching costs. People are used to their current OS. Switching involves learning a new interface, migrating potentially years of data and settings, finding alternative software, and risking incompatibility. These high switching costs make users very reluctant to move unless the new OS offers a truly compelling revolutionary advantage: economic viability and funding. Developing, testing, marketing, distributing, and providing ongoing maintenance and support for a modern OS requires massive, sustained financial investment, potentially hundreds of millions or even billions of dollars over many years. Securing that level of funding for such a high-risk venture, especially when users often expect OCs to be free or cheap, is incredibly challenging. Sheer technological complexity. Modern OCs are among the most complex software artifacts ever created, requiring deep expertise across numerous domains. Just assembling a team with the necessary skills is hard, let alone managing the development of millions of lines of code that needs to be secure, reliable, and performant. And it requires continuous maintenance forever. Regulatory hurdles, meeting modern standards and regulations for security, privacy, like GDPR, and accessibility adds further layers of complexity and cost.
So the outlook for a truly novel, general-purpose OS is pretty bleak.
Realistically, yes. The network effects enjoyed by the incumbents are just too powerful. That's why successful new OS platforms in recent decades have almost always been built on top of existing, established open-source kernels like Linux or BSD derivatives for Android, Chrome OS, Mac OS, or have been highly specialized for niche markets where the incumbents don't fit well, like RTOS for embedded systems, specialized IoT-OCs, or potentially future QS for quantum computers. Trying to build a direct competitor to Windows or Mac OS from scratch today is likely a fool's errand. Future innovation in the general OS space is much more likely to come from evolving existing open-source foundations or targeting these new specialized domains.
That really puts the current landscape into perspective. That table in the source summarizing these trends: cloud, AI, security, sustainability, quantum, digital divide, open source, and the challenges, paints a picture of a field facing massive disruption and opportunity simultaneously.
It's a field that's constantly being reshaped by both technological possibilities and pressing real-world needs. The OS isn't static, it's continually adapting. Conclusion.
Well, we have covered an enormous amount of ground in this deep dive. From the very dawn of computing and manual operations, through the eras of batch, multi-programming, time-sharing,
To dissecting the intricate components of the modern OS, the kernel, memory and process management, file systems, I/O, and exploring how we evaluate their quality.
and finally, looking ahead at the forces like cloud, AI, quantum computing, and the critical needs for security, sustainability, and ethics that are shaping its future.
It's really been a journey mirroring the entire history of computing. A relentless quest for more efficiency, more power, more accessibility, managing ever-increasing complexity, from managing one machine to potentially orchestrating global clouds or even harnessing quantum mechanics.
The operating system's significance clearly endures. It remains that fundamental layer managing complexity, enabling innovation in all other software, acting as the crucial translator between our intentions and the machine's execution.
It's the platform, the interface, the conductor. But the future path isn't simple. The challenges are immense dealing with the scale and distribution of the cloud, integrating AI responsibly, defending against hyper-sophisticated threats, minimizing environmental impact, bridging the digital divide, and maybe even figuring out how to manage qubits.
Yet those challenges also represent huge opportunities. The OS of the future seems likely to be more distributed, far more intelligent, perhaps self-adapting in ways we can barely imagine now. It will be pivotal in unlocking the potential of whatever new technologies come next.
Whether its core form remains a recognizable kernel, or evolves more into hypervisors, container orchestrators, or entirely new abstractions for quantum or neuromorphic hardware, those fundamental OS functions managing resources, enabling reliable execution, providing interfaces will surely persist.
So the operating system, in whatever shape it takes, remains a cornerstone of our technological world, constantly evolving and redefining what's possible with computation.
It truly is the hidden, vital engine driving so much of modern life.
It is indeed. And reflecting on that future, particularly the rise of AI within the OS, leaves us with a thought-provoking question for you, our listener, drawing from the implications in our sources. As AI becomes more deeply embedded and autonomous within operating systems, making proactive decisions about resource allocation, security responses, maybe even subtly shaping user interaction, what are the nuanced ethical dilemmas, perhaps beyond the more obvious issues of bias, privacy, and accountability that might emerge? How could an increasingly intelligent OS subtly influence user autonomy, choice, or even perception in ways we haven't fully anticipated yet?
It's a deep question. As the OS gets smarter, understanding the implications of its agency becomes critical.
Something to ponder. That officially wraps up this deep dive into the fascinating world of operating systems. We hope you found it informative and engaging. Remember, if you are curious about this topic or have any questions that came up, please do share them in the comment section below. We genuinely look forward to the discussion. It's always exciting to hear your perspectives.
Thank you for joining us on this exploration of such a complex but absolutely fundamental topic. It's a field that never stops changing.
You can find more deep dive like this right here on Silent Mind Studio. Thank you so much for listening.